This video covers trigonometric graphs. We're going to base a lot of our construction of these graphs on our knowledge of the unit circle. We're plotting on this circle the points that are found on the unit circle at our main increments of 30 degrees, 45 degrees, 60 degrees, and then the points that are on the x-axis and the y-axis. Now the equation for this unit circle is x squared plus y squared equals 1. That comes from a standard equation of a circle where the center is at the origin at 0, 0, and the radius equals 1. Let's go through and identify the x and y coordinates of each of these points. First here, definitely we're at 1, 0. Next, at 30 degrees, what I think about to remember all these ordered pairs is basically two main triangles, a 30, 60, 90 triangle, which I've drawn in here, and I know the lengths of these sides. The long side is radical 3 over 2, the short side is 1 over 2. I just have to have this triangle memorized, but this horizontal side is the x-coordinate, and the vertical side is the y-coordinate, so I know the ordered pair here is radical 3 over 2 and 1/2. The next angle measure at 45 degrees represents the other triangle I have to remember, a 45, 45, 90 triangle, and since these angles are equal, these two sides are equal. The x and the y coordinates are equal, and they are both radical 2 over 2. So the fractions I have to remember aren't too difficult either. It's a radical 1 over 2, which we can simplify to just be 1 over 2, a radical 2 over 2, or a radical 3 over 2. And if you wanted to get fancy, you could say that this 1 right here is a radical 4 over 2, which simplifies to 2 over 2, which is 1. If it helps you remember these ordered pairs, then go for it. Next measure at 60 degrees, it's again just the 30, 60, 90 triangle, but flipped over. So now my x-coordinate is the short side, the 1/2, and the y-coordinate is the long side, the radical 3 over 2. And back to this point now, our x-coordinate is 0, y-coordinate is 1. Now that we have these ordered pairs filled in, all the other ones are simply reflections of these points. So if I'm thinking about the next point here at 120 degrees, it's a reflection about the y-axis from this point here. If it's reflecting about the y or symmetric about the y, it means they'll have the same y value. So it will have another ordered pair with radical 3 over 2 for the y-coordinate, but the x value has its sign flipped from positive 1/2 to negative 1/2. So the rest of these points are all reflections. If I'm thinking down here in quadrant 3, like this point right here, it's in the middle on one of these diagonals of 45, a 135, 225 down here, but that's a reflection. So the x and y are radical 2 over 2, but have been reflected over x and y, so negative radical 2 over 2, x and negative radical 2 over 2, y. How about this point down here, quadrant 4? Either we're thinking reflections, or even I'm still thinking at this point about which of these triangles fits in. It's definitely a 30, 60, 90 triangle. My short side is horizontal, my long side is vertical. That helps me remember that the x-coordinate is the horizontal, so the x-coordinate is 1/2. The long side is vertical, so it's a radical 3 over 2, but since we're going down into quadrant 4, that must be a negative y-coordinate, a negative vertical distance. Now again, the graph we have here is simply the graph of a circle with radius 1, x squared plus y squared equals 1. Even though we know that in these ordered pairs, the x-coordinate is equal to cosine of the related angle, so this ordered pair would be cosine 30 degrees and sine 30 degrees, and that's the case for all of these ordered pairs. I could tell you from this point down here, which was 300 degrees, that cosine of 300 degrees is 1/2, sine of 300 degrees is negative radical 3 over 2. So we're using trig functions in here to see how these values work, but it's not really a graph of cosine or sine yet. To make that graph, we are going to use for our independent variable the angle. So we'll be marching along the circle, but our x-coordinate is going to now be the angle that we've rotated. And our y-coordinate, the dependent variable, will be cosine of that angle. We're still going to remember all of those ordered pairs as we fill in our table. At 0 degrees, what is cosine? So I'm thinking cosine is the horizontal coordinate. At this point right here, which is at 0 degrees, our x value is 1. And we'll just march along. So at 30 degrees, our x-coordinate is the long side, which is radical 3 over 2. Since I'm going to make a graph, we're using some decimal approximations. It's rare that I like to go with decimal approximations, and I'll keep reminding you of what the exact values are, but for this table, we're going with decimal approximations. And in fact, it is helpful to recognize some of these decimals. So this 0.87 I've rounded from a decimal number that starts with 0.866. So if you see that, it often is a result of a radical 3 over 2. Let's keep going around the circle. Next is radical 2 over 2. As a decimal approximation, it's 0.707. That's how I recognize those digits, and I rounded it further to 0.71. Next, 60 degrees, and now our horizontal is the short side of a 30, 60, 90. That's 1/2. And up here to 90 degrees, now our x-coordinate up there is 0. Okay, let's keep going along. Next is 120 degrees. Horizontally, I have to go back by negative 1/2. At 135 degrees, I'm going back negative 0.71, the radical 2 over 2. And at 150 degrees, I'm using the long side of that triangle, radical 3 over 2, negative, since I'm going to the left, the negative 0.87. And now at 180 degrees, x-coordinate is negative 1. Now you can see the repeating pattern of these values. We'll continue horizontally. This is negative radical 3 over 2, negative radical 2 over 2, negative 1/2, then 0. Now we're going to be using positive x values again, so at 300 degrees we're back to a positive 1/2. I don't have room here, but we know what these values are. At 315 we'll be at a positive radical 2 over 2, and then a positive radical 3 over 2, and then back to positive 1. What's important for us to know is that we could keep using increasing values for theta. I could have another point where theta equals 390 degrees, and then 405 degrees, and 420, and so on. So this graph doesn't stop after we've gone all the way around the circle, but a pattern that repeats has finished. But that pattern will continue to repeat for additional rotations around the circle. Let's start to plot these points. I'm choosing to use this graph here, which can handle y values between negative 1 and positive 1, and I say y values meaning the cosine theta, and our x values, the horizontal, is our theta measure. We're actually plotting theta and cosine theta, and each of these increments represents 15 degrees. I have to be aware that even though these are our main angle measures, they're not evenly spaced. They're 15 degrees apart here in the middle, but 30 degrees apart from these points that are on the x-axis and y-axis. So 15-degree increments will allow me to handle each of these numbers here. Okay, 0, 1, then at 30 degrees, so I've jumped 2, 15, 15, then 30 degrees, and I'm going up to the radical 3 over 2, approximately 0.87. And we'll continue to plot these points here, where our theta is horizontal and our cosine theta is vertical. Here we are at 180 degrees, and we've gone down to negative 1. At 210, we see our cosine values increasing again. Here's 270. There at 300 degrees, we're at 0.5. That's where our table ends, but we know those other values. We could fill those in. And that is one full rotation. We're back to 360 degrees, and cosine of 360 equals the same as cosine 0. It equals 1. But we do know that theta can continue to increase, and we'll get these repeating cosine values. So I'll fill in those dots there. And it can even go in the negative direction. We know negative rotations will go clockwise on this circle. So a rotation of negative 30 degrees will have the same value as 330 degrees. I'll try to connect all these points with a smooth line, but little short strokes is the key for me to trying to come up with a decent looking graph. And this is enough of a graph for me for now, because I'm able to see an entire repeating pattern. I don't need to see too much more than this. I understand that this pattern will repeat over and over and over again. So let's go ahead and construct the graph for sine theta. We're going to take the same approach, but as we go along the unit circle this time, since we're using sine, I'm looking for vertical distance, or the y-coordinate of each of these points. At 0 degrees, we've gone to the right 1, but vertically we've gone 0. At 30 degrees, this is now the short side of the triangle, the 1/2. Then we're increasing to radical 2 over 2. Then radical 3 over 2 is the 0.87. And then at this point here, our y-coordinate is 1. And continuing, now we're still positive in the vertical direction, but we're decreasing down to radical 3 over 2, radical 2 over 2, 1 over 2, 1/2, and then to 0. Now we're dealing with some negative vertical values because we're going down from the x-axis. A negative 1/2, negative radical 2 over 2, and so on. 300 is the last point on our table, but we can see the repeating patterns that the next one would be a negative radical 2 over 2, and then a negative 1/2, and so on. We're going to plot these points now, graphing theta and sine theta. Here's our first point at 0, 0. Now we're seeing the same values as we did in the cosine function, so we're going to have a very similar shape, but we should understand that the sine function crosses through the origin, but the cosine function crossed through the point 0, 1. That's a helpful way to keep the two graphs distinct, because otherwise they have a very similar appearance. Here we're finishing up the points beyond what we have in the table, including a negative rotation. Because it's working same way as cosine, we can use negative values. And connecting those points, there is our sine graph. It has the same shape, but it's crossing through the origin, where the cosine function crossed through the point 0, 1. Let's talk about this repeating pattern we first referred to in the cosine graph. We're calling this one period, and a graph that repeats, has one piece that repeats over and over again, is a periodic function, or a periodic graph. We're interested in identifying how far we have to go to be able to see one complete cycle. If we started at 0, at an angle of 0, we increased, we got back down here, we hit 0 again, but it's not a complete cycle because we didn't catch the part where we have the negative values. But once we get back to 0 here, now we have the part repeating again. So it took 360 degrees, or 2 pi radians, for the period. One strategy that people will use for measuring period is that we can go from peak to peak. If you go peak to peak, you're going to find a period that way. You don't have to be concerned about, well, I'm at 0 again, is it really the entire period? I mean, it's not too crazy to have to see, but peak to peak is another strategy we can use, and it will give us the same result, 2 pi, or 360 degrees. Here's a computer-generated graph of cosine. We can see this wave form, and we can see the period here. It's 2 pi. Starting at 0, 1, we go down to negative 1, and then back up to positive 1, and that covers, there's 90, 180, 270, 360 degrees. Let's take a look at the sine function. Same shape, because we saw those same function values, 1/2 radical 2 over 2, radical 3 over 2, and so on. But our initial point was at the origin, 0, 0. We still see the period is 2 pi, and we have this repeating periodic function. Here are those two graphs side by side. We can see that one is just a result of a horizontal shift by how many degrees? 30, 60, 90 degrees. Shifting the graph by 90 degrees can get you from a sine to a cosine if you shift to the left, or from cosine to sine if you shift to the right. While we're at it, we should take a look at the tangent graph and see this interesting shape. So let's construct this. We're going to start off by remembering these values on the unit circle, but when it comes to tangent, we're not interested in these coordinates x or y. Coming back to this unit circle diagram, and let's recall what our main x and y coordinates were here in quadrant 1. At 30 degrees, 45 degrees, and 60 degrees, we had these values of cosine and sine. Now, tangent can be defined as sine over cosine. So I can just simply do my sine value over a cosine value and see what that result is to come up with tangent. But that's doing a lot of division with fractions, or even worse with these decimals. Well, let's break down some important things to know about tangent. Remember this formula for calculating slope, y2 minus y1 over x2 minus x1. Now we're going to pick some random point on the circle. It's down here, and we know that our x and y coordinates on the unit circle are cosine angle and sine angle, and it's the angle caused by rotating from 0 degrees counterclockwise around to this point here in quadrant 4. I'll now think about a segment from the origin to this point, and at the origin we know that coordinate is 0, 0. If I choose to use the origin as my x1, y1, and cosine theta, sine theta as x2, y2, and put it into the slope formula to calculate the slope of this line, it becomes sine theta minus 0 over cosine theta minus 0, and that's sine over cosine, that's tangent. So we can think about tangent as a slope of the line that goes from the origin to the point on our circle that corresponds to some angle rotation. And since our x-coordinate is cosine and y-coordinate is sine, we will use y over x to calculate tangent. Now let's talk about making life easy when it comes to dividing these fractions. First, our slope at 30 degrees, y over x would be 1/2 over radical 3 over 2. We've got a complex fraction. We could simplify it in a few different ways. You could take the second fraction, flip it, and multiply because we know this big fraction bar is a divide. We could multiply numerator and denominator by 2, absolutely. What I want you to really recognize, though, about complex fractions is if ever these two denominators are the same, they basically cancel each other right out. And definitely those two methods I described will show us that very same result, but it can be a quick way to show that this is just a 1 over radical 3. Lose both of those small denominators of 2. Now let's do a rationalize the denominator, multiply top and bottom by radical 3. We get a result of radical 3 over 3. And for a decimal approximation, about 0.58. At 45 degrees, y over x, that's the same numerator and denominator, it equals 1. Or perhaps you even remember from first learning about slope that a 45-degree angle is a slope of 1. Next, at 60 degrees, slope y over x, we have a radical 3 over 2 over 1/2. Again, I'm losing those denominators of 2. It's a radical 3 over 1, or just radical 3, approximately 1.73. So these quantities aren't too difficult to memorize. Radical 3 over 3, and then the radical 3, and we'll know at the diagonal 45, 135, 225, 315, those all will have a slope of positive 1 or negative 1. And here, what I like to think about is, here's radical 3, and here is radical 3 divided by 3, so it's a smaller value doing that divide by 3. And I know about slope that the steeper the line gets, the higher the number is for slope. So the radical 3 is going to end up being where I have steeper lines. The radical 3 over 3 is where we have lines that are not as steep as the other ones. Let's fill in slope for our other points here. A pure horizontal line has a slope of 0, and a vertical line has a slope that is undefined. To come up with tangent for these other values, we're not interested in reflections because, again, it's not about the x and y coordinates. It is about slope. The first thing we could say is the slope of this line that goes from the origin to radical 3 over 3 through 30 degrees, it's going to have the exact same slope as a line that comes backwards this way into quadrant 3. It's one solid straight line, so if the slope up here is radical 3 over 3, the slope down here is also radical 3 over 3. So knowing quadrant 1, we automatically know quadrant 3. Slope of 1 at 45 degrees, so all the way back here at 225, it still has slope of 1. And here at 60 degrees, the slope is radical 3. Follow it all the way through the origin down here to 240 degrees would also have a slope of radical 3. Now what about quadrants 2 and 4? Let me start with quadrant 4 actually. Talk about the slope right here. If I haven't memorized that this not so steep line is a slope of radical 3 over 3, because it's going uphill, it's positive, then that same angle but going downward is the same kind of steepness but downhill. So it's still radical 3 over 3, but now it is negative. That's how I'll know about the tangent values in quadrant 4. So right here, downhill at negative 1, and now the steeper line here, it's going to be negative radical 3. And now when it comes to quadrant 2, I'm just following these all the way back. So here is a negative slope. It's not so steep, so it's the negative radical 3 over 3. Here it would be same slope down here, negative 1. And at this point here at 120 degrees, that follows all the way down to this, not that one, to this point right here, a slope of negative radical 3. So we're back to this setup where we have a table and we'll do the graph. I laid out degree measures, again, only till 300, bad planning. But we know there are repeating patterns to the values, so we'll be able to see exactly what we need with the table that we've got. Okay, we're thinking slope. So our first point is at a rotation of 0 degrees, and the slope of a line from the origin to that point, it's horizontal, so its slope is 0. Okay, next we're increasing our slope, so we're at radical 3 over 3, equal to approximately 0.58. Then slope of 1, then the slope of radical 3, and now our slope is undefined. Let's not put a number there. Now into quadrant 2, and remember, at this point here, I'm on a downhill line. It's the same value for tangent that I would get at this point down here, but I'm thinking a line from this point to the origin. It's downhill, so it's got a negative slope, and it's a pretty steep one. I know that this steep line was the radical 3, so this downhill steep has to be a negative radical 3, approximately negative 1.73. So we'll continue. Now we're downhill at negative 1, downhill with slope not so steep, negative radical 3 over 3, and now we're back to a slope of 0. Once we rotate into quadrant 3, we're back to uphill lines, a positive radical 3 over 3, then positive 1, positive radical 3, and now again at 270 down here, we're same as at 90 degrees, a slope of a vertical line that's undefined. Now 300, we're back to a downhill, a very steep downhill, negative radical 3 over 3, and so on. Let's plot these points. Okay, 0, 0, so another function that does cross through the origin. Sine and tangent cross through the origin. Cosine did not cross through the origin, crossed up here at 0, 1. Let's plot these other points. Again, my increments are 15 degrees, so at 30 I'm going up to 0.58 approximately. 45 degrees I'm up to 1. 60 degrees way up to radical 3, about 1.73. Now what should we have at 90 degrees where a value is undefined? And I like your answer if your answer was asymptote. Vertical asymptote, wherever we have functions that are undefined for that value of theta. Tangent of 90 degrees, undefined. So at 90 degrees, a vertical asymptote because the graph does not exist there. And now we're moving on to our next point at 120 degrees. We shot from a way up here with a positive high slope. Now we're down to a very negative slope, way back down here. And now we're increasing up to negative 1, a negative radical 3 over 3, then slope of 0, now some positive slopes. And we're at 270 degrees now, another vertical asymptote. There's our value at 300 degrees, and we have a repeating pattern. I filled in the next ones here. I filled in a couple in the negative direction because tangent also can handle negative angle measures, and it can handle angle measures that are in excess of 360 degrees. That's why we get the repeating pattern. Let's connect all of these, try to keep it smooth, more or less. Now, talking about period in this case, our repeating pattern did not require a full rotation around the circle 360 degrees. It only took halfway around the circle. Here we had in quadrant 1 positive slope. In quadrant 2 it shot down to negative slope. But once we got into quadrant 3 we matched up exactly with quadrant 1. We were repeating ourselves just after half of the circle. So period is only 180 degrees, and we could even count it. There's 30, 60, 90, 120, 150, 180 degrees, or pi radians. So it's important for us to know that the period for tangent function is only 180 degrees, or pi radians. For cosine and sine, it was 360 degrees, or 2 pi radians. So let's take a look at the computer-generated tangent graph, and there it is. The asymptotes are not put there for us. We could put those in just to really indicate where we have our period and where we have these values that are not allowed. One last thing I'd like to talk about quickly, I'm sure it will come up again, domain and range of these functions. Now with tangent function, domain, we're talking about as we move along the x-axis, are we seeing any breaks in the graph? And absolutely we are. Our domain is all real numbers except, let's see, this was 90, this was 270, this one would be 450. So we have all real numbers except starting with 90 and then other increments adding 180 degrees. A little bit of a complicated domain there, but definitely we've got values that are excluded from the domain. But how about range? Are we able to see values continuously all along as we move vertically? So yeah, we're getting very negative function values, we're getting zero function values, and we're getting positives. So range, all real numbers, but domain, not all real numbers. We've got some values to exclude here. And let's also talk about domain and range for sine and cosine. Here's our cosine function. First, domain. Are we seeing any breaks moving horizontally? No, it's totally continuous. We can define cosine for any angle measure. But what about range? What y values are we getting? We're only getting y values in between -1 and +1. So our range just from -1 to +1, including those endpoints, and domain all real numbers. And the graph of the sine function is working in a very similar way. It's got the same shape, just shifted by 90 degrees. Its domain is all real numbers, and the range only between -1 and +1, including those endpoints.